Okay, we'll get started here. Let's see, we'll work on these quiz questions. We'll finish up chapter 3. We should get to chapter 4. So we've got some quiz questions here, 15, 16, 17. So identifying this, let's see. Let's just cross some things out, and this is what you should do on the exam. Is this a synthesis reaction? And this is not, right? Because a synthesis reaction would be an A plus a B, and you get AB. Is this a combustion reaction? No, combustion reaction, you are for sure going to have, normally it's going to look like this. You've got some carbons, you've got some hydrogens plus oxygen, and you are going to get carbon dioxide plus water. It's not a combustion. Is it a decomposition? And it is not a decomposition, because for a decomposition, you'd have one reactant would be splitting up into at least 2 or more products. Is it a precipitation? Are we getting a solid for a product? No, we're not getting a solid. So that leaves us with the last one as we went there. Okay, for the next one, is the next one 16? Is it oxidation reduction? Yes, do not hesitate. Yes, 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 yes. Do not hesitate. Why? These, no charge by themselves, right? No charge. Then when they're in the compound, there's going to be a charge, and this is actually sodium hydride. So for sure, this is oxidation reduction. And this is oxidation reduction, and what else? Synthesis, right? We have 2 reactants turning into one product. So we have oxidation reduction and synthesis. This one here for sure is oxidation reduction. Why do I know that? Because I have oxygen here by itself, and that charge by itself is 0. And in the compounds, -2, -2. So whatever, it is oxidation reduction. And this is a classic oxidation reduction and combustion. Plus oxygen. Carbon dioxide and water. Okay, we're going to 24, 25. Let's see, 24. Okay, on 24, what is the correct equation for the base LiOH dissolving in water? Okay. So what is the charge of lithium? Always, always, always +1. What is hydroxide? -1, right? So if this dissolves in water, it is just going to split up into these individual ions. And if this splits up, and this is what we do in lab for part 1, we grab some stuff and we just see if it dissolves. It does dissolve, so it's going to split up into an aqueous cation and a -1 anion. It just splits up. Okay, let's look at 25. For 25, if we get a base, what do we need to get for a product? If we have a base, what do we need to get for a product? We have to get OH minus. We have to get OH minus. So the rest of these three are junk. So we're down to A or B. We are down to A or B because if you have base, you got to get OH minus. Now, if you get OH minus, we're going to write this out as a review shortly here. You would have CH32 NH plus, if you know you're going to get a base, write water as HOH. If you know you're going to get a base, we're going to write water as HOH, and this hydrogen comes off of the water. If this hydrogen comes off, leaves its electron behind, all it is a proton. So that is going to attach right here to this nitrogen. And we're going to end up with CH32 NH2 plus OH minus. Okay, it's a good idea if you're going to get a base to write water as HOH. And I think that works. 27. HClO4 is a strong acid and hence a strong electrolyte. Which of the following shows the correct equation for the ionization of HClO4? If this is a strong acid, what do we have to produce as a product? H3O plus or H plus, but typically H3O plus. You have to produce H3O plus. So A is absolute junk. I don't see H3O plus as a product. Right? If you have an acid, you're going to get H3O plus, junk. Let's go to the next page. There is only one equation that has H3O plus, and that's this one. So this is correct. If this is a strong acid, how many of these hydrogens will detach from the negative perchlorate? 100%, correct? That is the definition of a strong acid. How many hydrogens come off? It's not correct science, but that's the way to look at it. 100% of those hydrogens come off. Okay, so let's go with kind of that right there. We're going to review, and hopefully this review will help. So let's review a little bit from where we left off. We did this problem right here last time. It was the same thing we just looked at. HNO3 is a strong acid. How do I know it's a strong acid? Because you got two or more oxygens than hydrogens. And we wrote it out. I don't have it with me today, but we wrote it out like this. And we said that 100% of these hydrogens come off right here. 100%. So therefore, we are going to get H3O plus aqueous, and we get NO3 minus. That's where we left off. That's what we wrote, right? Thumbs up, vertical nods. Thank you. Okay. Well, let's do the ionization of nitrous acid. Is this a strong acid? No. It is not strong. So as soon as, and how do you know it's not strong? We only have one more oxygen than hydrogen, correct? So if this is a weak acid, how many hydrogens are going to come off? Not very many, very few, correct? Therefore, you are going to get few ions. Therefore, if we have a weak acid, you would have HNO2 aqueous plus H2O liquid. That is the same. We don't do a one-way arrow. We do double arrows like this. Those are our equilibrium arrows. We are still going to get H3O plus, and we are going to get some H3O plus and some NO2 minus. But over here, we get few ions. Strontium hydroxide is a strong base. What is that going to do in water? If you have a strong base, you have to get hydroxide ions, right? So this is what we did for lab this week. We could have used this as a solid. No, I actually put it as a solid for here. 100% splits up into its ions. So in this case, strontium is always +2. So floating around in solution, strontium +2 aqueous plus, there's where students really make, oh, not good. No, it's just not good. This produces 2 OH minuses. Don't keep OH with a 2 there. This is going to split up into 2 hydroxides. Strong base. So 100%. 100%. Letter D is like our quiz question. This, if it's a weak base, if it is a weak base, in the word base, what do you have to produce? OH minus. So we'll write that out. We have CH3 NH2 plus, write water as HOH. If it is a weak base, we're going to get just a few ions. We write an equilibrium like this. That hydrogen comes off. So we get CH3 . This hydrogen comes off, leaves its electron behind. The hydrogen only consists of 1 proton and 1 electron. If it leaves its electron behind, it has a plus charge. That is why we always get a plus charge here. If it leaves its electron behind, that's always why we get a negative charge here. This is a weak base. If it is a weak base, we are going to get few ions. Okay, so that's kind of a summary. Strong acid, all of the hydrogens come off. Weak acid, a few hydrogens come off. Strong base, all of the hydroxides go into solution. If you have a weak base, you get few ions and you get a few hydroxides in solution. Okay. On your pink sheet, it tells you if you have a strong acid or a strong base as well. Those rules are on there. Okay. Now we just have to finish up, I believe, page 16 here, and we're going to be done. So this is 3-7 gas forming reactions. Okay, so there's a generic way to look at these. So if you have a metal carbonate, so X represents a metal, or if you have a metal bicarbonate. A carbonate is CO3. Bicarbonate is HCO3. And reacting those with an acid, and with an acid, you know you've got a +1 charge on the hydrogen, but you have this negative ion here. You produce a salt, carbon dioxide, and water. This is our gas. It's gas forming reactions. It's carbon dioxide here. So let's look at our generic example. This is a metal carbonate, and the X can be many metal ions, sodium, potassium, lithium. This is our acid, HY. We're going to get XY. This is our salt, carbon dioxide, and water. If we have a metal bicarbonate plus an acid, we still get the same products. So here's an example: sodium carbonate plus our acid. Let's see if we can follow this now. What is our X? Our X is sodium ion, correct? What is our Y in this case? It's that chloride there. So what do we get? We get XY. That's why we get sodium chloride +1 and -1, and then carbon dioxide and water. Just given. And on the next one, if we follow it, our metal is sodium again. Our Y is exactly the same. It's a chloride. This is hydrochloric acid or hydrogen chloride. Sodium +1, -1, carbon dioxide, and water. So we get a gas forming reaction. Here is our gas we get, right? Carbon dioxide. Okay, so that's a metal carbonate or a bicarbonate. If we have a metal sulfite, so X is a metal again. Now, sulfate is SO4, sulfite is SO3. You know, I should put the charges in here. I apologize. Sulfite's -2. Let's go up here and put these in. Carbonate is always -2. Bicarbonate is -1. So this time we have a metal carbonate plus an acid, HY for an acid, starts with hydrogen. We know we have an acid. We get a salt, XY, but instead of carbon dioxide gas, we get sulfur dioxide gas and water. So here's our generic reaction. This is a metal sulfite. This is our acid. This is our salt. So I use sodium as an example again. Actually, this is from the table 3.2 in your book. So we have sodium sulfite. And sodium is +1, sulfite -2. So that's why we get Na2SO3, hydrochloric acid again. So my Y is chloride. So my XY plus SO2 plus H2O. Then we have a metal sulfide. Again, X just represents a metal ion, sodium, potassium, lithium, calcium, barium, whatever it is. So if we have a metal sulfide and acid, we get a salt and we get the stinky rotten egg H2S. So X, and then sulfide's always -2. So metal sulfide. So here's my example from the textbook again. Sodium sulfide. My Y is chloride. So there's my XY. Okay, let's do this owl example here. And then I think what we're going to do is we'll go to the quiz for the last 3 questions, and I'll help you out with those. All right, this owl example. Ugly. Oh, I've got it entitled ugly. It's getting ugly. It says, write the net ionic equation for the reaction that occurs when barium carbonate reacts with excess nitric acid. All right, so this is an XCO3 metal carbonate, right? In fact, let's write the correct formula out. What is the correct formula for barium carbonate? Well, we've got Ba+2, and carbonate is always CO3 -2. Right, so we just have barium carbonate, and it's a solid. So that's going to be our starting box here. And I guess I'll just write that in. BaCO3 solid. Nitric acid. Now, as soon as you see the word acid, we want H+1. And you are going to be looking for nitrate on your pink sheet for the ion. 8 has been changed to ic, nitrate. And nitrate is NO3 -1. And that is aqueous. I'm not sure why I'm switching colors, but. And this is my generic is, this is an HY, right? Sorry. So we have an XCO3 plus an HY. So let's fill this in. So now let's split this up. So this solid states that we need the net ionic. So Well, let's finish this off. We can leave it like this and fill in the boxes here. Let's do the complete reaction first. So I'm going to draw an arrow here. This is kind of lined up right. Okay, so I have an X CO3 plus HY. I'm going to get XY. So where's my XY? I'm going to get. I'm going to get barium. Barium's my X, right? So I'm going to get barium. My Y is nitrate, NO3 minus. So I'm going to need 2 nitrates. Is this going to be aqueous? Is this going to be aqueous with what we did for lab last week, our solubility rules? Yeah, you don't need to look. Why don't you? Because it's a nitrate. Nitrates are going to be aqueous. I'm going to put an AQ here. And the rest of my products are carbon dioxide gas and liquid water. And these are just given. Now let's do this complete ionic. Let's do our complete ionic reaction because it wants net ionic. So for complete, whoa, we got to balance this, don't we? Whoa. What do we got to do to balance this pig? We got 2 9. We're going to have to put a 2 in front of this, right? We have 2 nitrates. And let's see, that gives us 9 oxygen. We've got 9 oxygen. I think we're good. Yep, we're good. Now let's do a complete ionic. That'll be a good review anyway. So this is a solid. It's going to stay together. This HNO3, and what Al does, and I believe, yeah, what Al does is it's going to split this up into 2 H plus aqueous plus 2 NO3 minus aqueous. Nitric acid, 2 H pluses and 2 NO3 minuses. Barium nitrate is aqueous, so we're going to get Ba plus 2 aqueous plus, and here's where I see things go awry for lab. Students want to keep this together. There's no such thing as an NO3 2 ion. If you're not sure what these things do when they split up, it should match what's on your pink sheet. If you look under the ends, you are going to see NO3 minus. So you're going to get 2 nitrates. These are not ions, so they stay together. So we're going to have plus CO2 gas and plus H2O liquid. All right, let's look for some spectator ions. And my spectator ions, I've got 2 nitrates here. And I've got 2 nitrates over here. And that's all I can cancel out. So I'm going to put a light X through these. Now I'm going to be left with my net ionic. So I'm going to have to redo my 2 boxes over here as best I can, because my answer is going to go here. Let's see. This is a small box. I don't need a very big box here. Okay. So the answer is going to be barium carbonate solid. Plus 2H plus aqueous then we get Ba plus 2 aqueous carbon dioxide gas water. For our net ionic. Like that should do it. It's kind of ugly. But remember, we're only splitting up anything that's AQ, we're splitting up. Okay, let's go to, that finishes this up, chapter 3. I think we got the next page covered, right? Yep, oxidation reduction, we got that covered. Yeah, we're good. Yeah. All right, so let's look at your quiz. So we're at 28, 29, 30. Let's look at these. If you look at the test outline that I sent you in an email, I didn't put very many of these on a test. I think 1, maybe, not a lot, but there is 1. Okay, it says finish the gas forming reaction. So this, let's follow this generic reaction. It's an XS plus an HY. And the first thing we should do is write out what we get. And that's what we just did here on page 16. It's an XS plus an HY. We're going to get XY plus H2S. We should get XY plus H2S gas. Well, right away, there's only one that's going to work. There's only one correct product. All right, there's only one there that's going to work. Let's look at the next one. We have XSO3 plus HY. We should get XY plus SO2 plus H2O liquid. That's our generic reaction that we should get. So it looks like we have 2 possibilities, right, that match This one produces SO2 and H2O, and this one produces SO2 and H2O, right? So B and D, I don't know, B and D are just garbage, right? B and D are just garbage. Well, we've got calcium sulfate. What's the charge? What's the charge of calcium? So calcium's always positive 2. Sulfite minus 2. Hydrogen is positive 1 and nitrate is minus 1. So when we do our XY, when we put together our XY, X is going to be calcium plus 2, and our Y is going to be nitrate minus 1, right? We put this together. So we need 2 nitrates, right? We need 2 nitrates out of this, so we would have a parenthesis, a 2 for that. All right, let's look at 30. In 30, we have an XCO3 plus an HY and we should get XY plus CO2 gas plus H2O liquid. So this looks pretty good as far as this much looks pretty good, huh? Those 4 match up, CO2 plus H2O liquid. So let's see what we've got here. Plus 1 and minus 2, lithium carbonate, plus 1 and minus 2. So that's why we have Li2CO3. Plus 1 and minus 1. So my X is Li plus 1. And my Y is NO3 minus 1. And that's it. That for sure is going to be aqueous plus CO2 gas and H2O liquid. And then we just have to balance that, right? And we got 2 lithiums here. Two lithiums there. Two nitrates here then. I think that balances out. Okay. That should help you finish up the quiz. The quiz is due Sunday night along with OWL Chapter 3 Part 2, correct? OWL Chapter 3 Part 2, yes? Sunday night. Okay. That outline that I did for you for the test is absolutely spot on. Because students ask me, well, do I have to memorize a bunch of people? And it was like, You know, we talked about Rutherford and Thompson and all those. Yeah, I think I've got one or two on there, correct? But it is absolutely specific on that outline. I think I went through the test line by line by line. So make sure you're looking at that outline that I sent you. Okay, now this is where we're going. No, not this one. This is where we are going now. Chapter 4. So I want to do 2 questions here before we go. So this will start chapter 4, part 1. And this is not on the test, right? Chapter 4 is not on the test. But let's introduce you to this and where we're going. We just looked at a bunch of reactions from the last chapter. We did a bunch of reactions like this. We talked about whether or not the reactions are synthesis, decomposition, single replacement, double replacement, etc. We looked at oxidation, reduction, reactions. And right here is more, here's kind of the summary for reactions. Now, we also did moles. We did grams to moles, moles to grams, and so on. So now we are going to put the numbers to the reactions, which is stoichiometry. Right? Stoichiometry or stoich is taking reactions and really putting the numbers to them. It's something like this. I've got aluminum plus iodine. I'm making aluminum iodide. What's my is this oxidation reduction? For sure, yes, right? What's my charge of aluminum? These are aluminum atoms. There's no charge. This is iodine, molecular iodine, no charge. What's my charge here? +3 and -1. So that's oxidation reduction, a synthesis reaction. And we know this, from this balanced equation, everything reacts according to moles, which means this. I need 2 moles of aluminum to react with 3 moles of iodine. And I'm going to produce 2 moles of aluminum iodide. That is my ratio, 2 to 3 to 2. Okay. Now, I'm going to show you a different way that you've done this in the past, more than likely. Please try it. Don't just block out, oh, my high school chemistry teacher, he showed, no, just watch this. I make it so easy. It is so easy. So we are going to reserve grams for up above. So down here, I already have grams typed in. Grams go up above, moles go on the bottom. So it says how many moles of iodine react with 0.429 moles of aluminum. 0.429 moles right here. Put it down here. 0.429 moles. I want you to put a box around it. We put a box around it because we know that's our starting moles. Now, how many moles of iodine are needed with a 2 to 3 ratio? Anything else I figure out from my starting moles, I put it in an oval for moles. Now, we just draw an arrow. When you draw your arrow and point your arrow to the moles you're trying to figure out right here, The balanced equation moles number goes on top. 3. What you're coming from goes on the bottom. You're just making the mole ratio fraction. You're just doing the ratio. That's it. Please look at this. Look at the simplicity of this. I need to figure out how many moles of iodine. I draw my arrow. When I point my arrow, that number from the balanced equation goes on top. The pointed arrow part goes on top. The start of the arrow, where I started from, that balanced equation number goes on the bottom. That's all there is to it. I take 0.429, I multiply it by 3, and I divide by 2, and this is 0.644. Now, what if I wanted my moles over here of aluminum iodide? No big deal. I'm going to come over this. I'm going to draw an arrow here now. I'm going to start with this moles again. Look at the simplicity of this. Please, please, please look at the simplicity of this. When I point my arrow there, what number is going on top immediately? This 2, correct? 2. And where I started from is this 2. 2 over 2. How many moles of aluminum iodide am I going to produce? 2 over 2 is the same as 1, and that is 0.429 moles. Okay, I will stop right there. We will continue here Monday, test Wednesday. Have a great weekend.